Hello and welcome to ENCS 6010 Advanced Applied Mathematics class. This will be our lecture 2. My name is Ali Sekmen. I'm a professor of computer science at Tennessee State University. Let's get started. Okay, again, this is for ENCS 6010 Advanced Applied Mathematics. The topic is subspaces. We will specifically talk about what a subspace is, and we'll define certain properties of subspaces, such as being linear, disjoint, complementary, or orthogonal. And we'll talk about important concepts such as subspace angles and distances between subspaces. So we're going to define and measure how close the subspaces are to each other. In the last lecture, we talked about inner product spaces, and we said that inner product spaces, we have an analogy to Rn. The inner product is a kind of measure of an angle between two vectors in the inner product space. We talk about normed vector spaces, and we defined a norm. Norm was a measure of the length of a vector in the norm vector space. And we said that length is not as strong as angles. We talk about metric spaces. In metric spaces, we define what a distance is. And we said that distance is not as strong as length. And then finally, we talk about topological spaces. And we said that there might be some spaces in which we may not define angle, length, or distance, but we can still define how close the elements of topological space are. And this was based on neighborhoods concepts. So you can define nearness based on the neighborhood concepts using in the topological spaces. And we had this big picture. We said we have Hilbert spaces, and Hilbert spaces were Hilbert spaces are inner product spaces, and then we had Banach spaces, which are normed vector spaces. We said that every Hilbert space is a Banach space, and every Hilbert space is an inner product vector space, and every Banach space is a norm vector space, and every inner product vector space is a norm vector space. And this was one picture. Second picture, we said that we have inner product space, and from an inner product, we can always define a norm. Therefore, an inner product space is a normed vector space. And from a norm, we can always define a metric, a distance. Therefore, a normed vector space is also a metric space. And from distance, we can always define or induce a topology. Therefore, a metric space is a topological space. And but we said that there might be some infinite dimensional vector spaces in which we may not induce a topology. So there are some vector spaces which are not topological spaces. So what's a subspace? Let's remember this. Assume we have a vector space V with vector addition and scalar multiplication operations. Remember, we had 10 axioms that needs to be satisfied for a set to be a vector space. And now let's assume that we have W. W is a subset of set V. Okay. So how do we know that W is a space? Are we supposed to check all those 10 axioms? No. If we know V is a vector space, and if W is a subset of set V, all we have to check is if the elements of W, or if the W is closed with respect to vector addition, and if W is closed with respect to scalar multiplication. That's the lemma that we said. If W is a subset of V, then W is a subspace if it is closed with respect to addition, vector addition, and it's closed with respect to what? Scalar multiplication. Okay, and this is one example. We are in R3. We are in R3, as you see here, and we have a plane and we have a line. We said that a line is a subspace of R3. Why? If you pick two elements, for example, this one and this one, if you add them up, you're going to end up with another element on the line. So that means that's closed with respect to vector addition. And if you pick any element here, and if you multiply it by a scalar, it's going to be still on the same line that is closed with respect to scalar multiplication. So therefore, this line is what? A subspace of what? R3. So basically, this line is a subspace of what? Is a subset of R3, but it's also what? A subspace of R3. Similarly, we have a plane, but it's important that it passes through origin, okay? Because it needs to have what? The identity element, which is 0 element with respect to vector addition. And if you take any 2 points like this and that, if you add them up, you're going to end up with another point on the plane. So it is closed with respect to addition. And then if you get any point here and multiply it by a scalar, it will be still on the plane. So plane is a subset of R3, but it's also what? A subspace of R3. And the dimension will be what? 2 for plane, and for line it is 1. So line is a one-dimensional subspace, whereas a plane is a two-dimensional subspace of R3. All right, let's talk about sum of two subspaces. Okay, assume that X and Y are subspace of a vector space V. Okay, so that means X is a subset of V, but also a subspace of V. Y is also a subspace of what? V. Then the sum of X plus Y, X and Y, is defined as all possible sums of vectors from X and Y. This is what I mean. So the sum of X and Y, the sum of two subspaces, consists of all elements. The sum of all elements, the first one comes from the first subspace, the second one comes from the second subspace. Okay? It is important to understand that the sum of X plus Y is a subspace of W. And let's see why. Sorry. Okay. So the sum of X and Y is a subspace of Y. Well, because if you pick any element in this sum, let's assume that you pick an element Z, which is in this sum. If you pick another element, let's say W in this sum, if you add them up, Z plus W, obviously that will be also in this sum. Okay, so if you take any element in this sum, if you multiply it by a scalar, clearly that will be also what? In the sum of the subspaces. So therefore it's closed with respect to addition, and it's closed with respect to scalar multiplication. Therefore it's a subspace of what? V. Okay. Union of subspaces. People typically get confused with sum of subspace and union of subspace. Let's be very careful here. Now X and Y are subspace of a vector space V. Then the union is defined as all elements that comes either from the first subspace or from the second subspace. The union of X and Y may not be a subspace itself. Okay? Why? Think about this. Assume X is this line. Assume X is this plane, which is a two-dimensional subspace of R3. Okay. So basically here what I'm saying is X is the plane, Y is the line, okay, and V is simply R3. As you see here, X plane is a subspace of R3, line is a subspace of R3. Now, when I look at the union of that, that means all the points that comes either from the plane or from the line. So for example, Z1 is in the union, Z2 is in the union. But if you add them up, for example, if you get, this is Z1, this is Z2, if you add them up, Z1 plus Z2 may not be on the line or may not be on the plane. Therefore, the union of X and Y is not a subspace in this case. So it's not closed with respect to vector addition. Okay, here Z1 is in the union, Z2 is in the union, but if you add them up, it is not in the union. It is somewhere else, not in the plane, it's not on the line, somewhere else. Okay, how about intersection of two subspaces? Again, if we have two subspaces, then intersection consists of all elements which are on Z, which are on the first subspace as well as on the second subspace. So that's the intersection. The intersection of X and Y is a subspace of V. Why? I mean, that's pretty easy. And for example, if we take Z1, which is in this, and if we take another point in the intersection, if we add them up, obviously the summation must be also what? On the intersection. This is very clear. So therefore, X intersection Y is a subspace. Similarly, I mean, if you multiply Z1, it is supposed to be in the intersection as well. So it's closed with respect to addition and closed with respect to scalar multiplication. Here's an example, actually, okay? And assume this plane is X, this plane is Y, okay? What is intersection? Isn't it a line? For example, here, this line, or here, this line. That's the intersection. And if you take 2 points in this line, if you add them up, they will be still on this line. Or if you take a point and multiply by scalar, it will be still on this line. Okay? So let's talk about complementary subspaces. Okay, so this is kind of not displayed well on this presentation mode, but well, I'm going to tell you what it is. Okay, so think about this. If we have two subspaces, X and Y, okay, and each one is a subspace of V, we call them complementary if V is the sum of those subspaces and the intersection of those two is empty set, okay? So basically, for example, think about this plane here, okay, and think about this line here, okay? So if you take any point in R3, okay, let's assume that in this case, let's assume this is R3, let's assume this is line, let's assume this is the plane. Okay, but always keep in mind, I mean, we are only giving examples in R3, but our space is never R3. The space might be very high dimensional, maybe 1,000 dimensional. It's not necessarily 3-dimensional. Just for visualization purposes, I'm always using R3 so that you can see it. Okay, so let's see. If we take any point in R3, any point in R3, like here, we can always write this point as sum of two vectors. One may be coming from this plane, another one might be coming from this line, okay? So it's always, we can always write this point, express this point as sum of what? 2 points. One comes from the line, one comes from the plane. Therefore, we say that V is the sum of X and Y. Additionally, the line and the plane intersects only where? Only at the origin, as you see here. So the intersection is an empty set. They do not intersect. I mean, that's only the identity element. Therefore, we say that in this case, line and the plane are complementary. And we say that V is direct sum of X plus Y in this case, okay? If the intersection is 0, then we call X and Y as direct sum of, or V is said to be the direct sum of what? X and Y. What does that mean? For any V, in V, there is a unique vector. There are unique vectors. One comes from X, the other one comes from Y. There's only one way to represent V. Okay. However, if this was two planes, the situation will be different because the intersection wouldn't be what? Empty set. Okay. How about orthogonal? Okay. Well, sorry about the presentation, but I think this should be fine. I can express this. Let's assume X and Y are again subspace of an inner product vector space this time. Not any vector space, but X and Y are subspace of inner product vector space. Why? Because I'm going to use the angles this time, okay? And think about this plane on XY, and then think about this line on Z, okay? So, and if we take any vector on the plane, and any vector on this line, and if you look at the angle between them, it's always what? 90 degrees. In other words, the inner product between any vector in this plane and any vector on this line is always what? 0. So we say that X and Y are orthogonal if here what we have is, we have XY is 0 for all X in X and for all Y in Y. So if you pick any vector in the plane, any vector on the line, if the inner product of those two are 0, then that's X and Y are orthogonal. I hope this is clear. It's important. Orthogonal subspaces are important. Okay, if X is a subspace of an inner product space, X perp is orthogonal complement if X direct sum X perp is V. What does that mean? Look here. If I R3 can be written as direct sum of line and plane. Is that correct? Because any vector in R3 can be represented in a unique way, one vector from the line and one vector from the plane. And additionally, if the line and plane are orthogonal, just like in this case, then we say that V is direct sum of what? X and X perp. Here, X is line and orthogonal complement of line is plane. Okay, and then R3 is X direct sum X perp. Orthogonal complement means what? Think about a subspace and think about another subspace. If the inner product of any two vectors from those two subspaces is always 0, that means they are orthogonal to each other, right? And if the dimension of the sum of the dimensions of subspaces is equivalent to the dimension of the enclosing space, then they are orthogonal complements. For example, here, dimension of line is what? 1, and then dimension of plane is 2, and if you add them up, you end up with what? Dimension of R3. Okay, so what's orthogonal projection? Think about, again, assume we are in, assume that M is our subspace in this case, okay? So, and then assume that this is the orthogonal complement of what? Orthogonal complement of M. For visualization purposes, again, I put as a plane and a line, but again, think about high dimensions. So M is our plane, is our subspace, and this is the orthogonal complement of the subspace. And assume that V, this V, can be written as sum of two vectors. One comes from subspace M, and another one comes from the orthogonal complement of the subspace. okay? And then M is called orthogonal projection of V on subspace M, and N is called orthogonal projection of V on M perp, or orthogonal complement of M, okay? And projector PM is a linear operator such that, for example, what you do is you have vector V. If you apply this linear operator on this, you end up with M, okay? All right, or if you apply this to V, you end up with the component on M perp. Okay, that's orthogonal projection. Let's talk about independent versus disjoint subspaces. Think about a line. Assume we are in R2, right? This is R2, and we have line, and line is one-dimensional subspace of R2. If we have another line, if they intersect only at the origin, now we have two lines that intersects at the origin, and the dimension of this line is 1, dimension of this one is 1, 1 plus 1 is 2, which happens to be the dimension of R2, right? So let's keep that in mind. So we have two lines that intersect at the origin. And if I take any point in R2, I can always find one vector from here, okay? One vector from here and maybe another vector from here. If I add them up, I will end up with this. So that means any vector in R2 can be represented as a unique combination of one vector from line 1, another vector from line 2. Okay, let's keep that in mind as well. Okay, so these two lines are disjoint because they only intersect at the origin, but they are also independent. Okay, for example, if you take a point in this line, there is no way that this line, this point, can be written as a linear combination of points from the other line. There is no way for that. However, if you consider three lines, think about three lines. They intersect at the origin. So that means these are disjoint, but they are not linearly independent. Why? Because if you take a point here, you can always find maybe one vector from there and another vector from this line. And if you add them up, you can bring this up. So that means a point in one of those lines can be written as linear combination of the points from other two lines. So they are not linearly independent. And again, now this time when you look at the dimensions, this is one-dimensional, this is one-dimensional, 1. If you add them up, which is 3, bigger than what? 2. 2 was the dimension of R2. So let's keep this one in mind. So how do we check if subspaces are independent? Assume that we have S1, S2, Sk subspaces of Rn. So we have K subspaces. And if I look at the sum of those subspaces, like S1 plus S2 all the way to Sk, and if I look at the dimension of the sum of those two subspaces, if it is equivalent to sum of the dimensions of subspaces separately, then they are linearly independent. For example, we had one line, another line, okay? Line 1, line 2. And if I get line 1 plus line 2, that's basically R2. That means dimension of line 1 plus line 2 is the same as dimension of what? R2, which is 2. So here it is 2. And then dimension of first line is 1, and dimension of second line is 1, and 1 plus 1 is equal to 2. That means two lines are linearly independent. However, if we have three lines, 2, 3, line 1 plus line 2 plus line 3, this is still R2. because it spans the whole space, whether 2 lines or 3 lines. As long as you have more than 1 line, it's going to be what? R2. And if you take dimension here, that means dimension of R2. So this will be what? 2. So that means this is 2. But then we have first line, we have second line, and we have third line, which is 3. So 2 is not equal to 3. Therefore, 3 lines are not linearly, or they are not independent. Okay. And subspaces S1, S2, Sk are disjoint if they intersect only at the origin. Okay. So which one is stronger? Of course, independence is stronger. Independent subspaces are definitely disjoint. However, not all disjoint subspaces are independent, as we have seen in the example of lines. Now we are going to talk about angle, minimal angle, but let's motivate ourselves a little bit on that. So what does this mean? Think about 2 vectors in R2. Assume this is vector F, assume this is vector G, and this is the angle. And assume we are in what? R2. And if you recall, F inner product G was length of F, length of G, and then cosine theta, right? What if the length of G is 1 and length of F is 1? Then the inner product FG will be simply what? Cosine theta. In other words, theta would be arc cosine FG, right? So that's in 2 dimension. And so the minimal angle. So if we have all those vectors, many of them, like if you take any vector F and G, and whichever, and each one has an angle, right? Theta 1, theta 2, theta 3, and so on. And the minimum angle will be whichever statement that minimizes or maximizes this, because cosine, for example, cosine 0 is 1, but cosine 90 is 0, right? As the angle gets bigger, cosine gets lower. So now let's go back and see what does this mean. Assume F and G are subspaces of RD. Right? The minimal angle between F and G, between 2 subspaces, is defined as, by the way, this is another notation for F inner product G, okay? So F transpose G, because when we deal with RD, it is because if you remember, this was equal to what? Fi, Gi, I from 1 to dimension D. And in matrix notation, you can always write this as F1 all the way FD, G1 all the way GD. That means F transpose G. So they are equivalent. When I say this or that, they are exactly the same thing. Okay, so what does it do? Assume we have 2 subspaces. The minimal angle between those subspaces is defined as whichever we do arc cosine. Think about all inner products of 2 vectors. Lowercase f comes from the first vector space, G comes from the second vector. Think about all inner products. That means look around all angles, basically, and get the minimum of those angles. So that's the minimal angle between 2 subspaces. For example, here, assume that this is F, the line, assume the plane is G. What does that mean now? That means take all the possible vectors on G and all possible vectors on F and find the angles between them. For example, here, if this is a vector here, if this is another vector, that's the angle between them, okay? However, if this is a vector there, if this is another vector here, that's the angle between them. So angles are different. Think about all possible angles between all possible vectors. One comes from first subspace, the other one comes from second subspace. Get the minimum of those angles. Okay, so it is good. It's a good measure for complementary subspace. For example, here the plane and line, they are complementary subspaces. The sum of this line and this plane gives me what? R3. And it's nice. For example, the minimal angle in this case will be most likely, you know, this angle right here. Okay, so it shows the minimal angle between the line and the plane. So that's a very good measure. However, it's not very useful when the spaces are not complementary. For example, here, why are those two are not complementary? Assume this is F, assume this is G. Dimension of F is 2, dimension of G is 2, 2 plus 2 is 4, which is not equal to 3, dimension of R3. So that means F and G are not complementary subspaces in this case, okay? Well, what is intersection? Okay, so what is the minimal angles? Think about all vectors on this plane. Think about all vectors on this plane. And what will be the angle, the minimum of the, for example, here, this line is on this plane, on the blue plane. But that line is also on the yellow plane, right? So if I take two vectors along this line, one will belong to the blue, the other one will belong to yellow. And the angle between them is obviously 0, right? So if the spaces are not complementary, the minimal angle will be 0. So that's not very useful in our case. So minimal angle is useful if what? Subspaces are complementary. Otherwise, minimal angle does not tell us much. So what will be useful for non-complementary subspaces? Maybe you can define gap between two subspaces. Think about this yellow one is our F, blue one is G, okay? So we define gap. First, we define distance between F and G, between F and G. What does that mean? Think about a unit ball on G. Think about a unit ball on G. What does unit ball means? That means the points on this ball have length what? 1. So that means the norm of all the points on this ball will be what? 1. 2 norm, okay? And the distance between F and G is defined as, think about all the points and get their projection on F. Projection will be this, right? But I'm going to talk about, this is the projection. I'm talking about this distance. This is what distance between point G and F. And think about all distances between all points on the unit ball and F and get the maximum of them. For example, here, if G is this one, distance is what? 0. If G is here, distance will be that one, and the maximum distance will be right here. So get the maximum distance. So this is between F and G. Similarly, you can define distance between G and F. This time you have to take a unit ball where on the yellow plane, but you can also do that. The gap between two subspaces defined as what? Minimum of distances, distance between F and G and distance from G and F. By the way, distance from F and G and F are not required to be the same for obvious reasons. If you pause the video and look, you will see that. So, well, this is a good measure, right? This is pretty good measure for non-complementary subspaces. Okay, so that's called maximal angle. The maximal angle between F and G is defined as what? Define the gap between F and G and do what? If we go back here, and for example here, okay, this is the distance, and this is 1. Sorry, this is 1. Okay, hold on, let me be clear here. So if you guys look here, okay, let's use blue. This angle is, this is orthogonal, okay, and we know this is 1. Then this must be what? If this is theta, this is equal to sine theta, okay? So theta will be arc sine distance between F and G. So here, let's go to the next slide again. The maximal angle in this case defined as what? Arc sine of gap between F and G. Now with the minimal angle, and then minimal angle was good for complementary subspaces. Maximum angle is good for what? Non-complementary subspaces. Well, there are other angles that you can define between minimal and maximal angle. And I call principal, I think I was supposed to principal angles, okay, of two subspaces. Please pause the video here because you have to look at it a little carefully. So F and G are subspaces of RD, and assume that K is the minimum of two dimensions. For example, if you have a line and have a plane, dimension of line will be 1, dimension of plane is 2, and think about the minimum of them is 1. Or if you have a subspace of dimension 3, subspace of dimension 5, minimum will be what? 3. Because the dimension of subspaces may not be the same, but think about the minimum dimension of those two subspaces. Let's say that that's K, okay? Then you can define K principal angles. So what does that mean? For example, if you have two lines, dimension is 1, dimension is 1, so K is 1, and we have only 1. That means between two lines, you can define only one angle, and it makes sense, right? But if we have a line and a plane, again, if you have a line and a plane, and line is one-dimensional, plane is 2, minimum of them is 1. Again, if you have a plane and if you have a line, it makes only sense to define one minimal angle, one angle between them, theta 1. And therefore, we have only theta 1. However, if we have two planes, dimension is 2, so that means K is 2. Then we have to define theta 1 and theta 2. What are they? If this is one plane and if this is another plane, and one will be 0 because that's the intersection. If we recall, that's the minimal angle. This one will be 0. The other one will be the maximal angle we just defined in the previous slide. So it makes sense to define minimal and maximum angles in this case. But if the dimensions are not the same, for example, if one is 20-dimensional, the other one is 15-dimensional, then we can define 15 angles between them, okay? And the angles will be between 0 and 90 degrees, pi over 2. And angles will be, theta 1 will be less than or equal to theta 2, less than or equal to, all the way to less than or equal to theta 15, okay? So that's how they are ranked. But let's see what it means. I know this sounds like a very, confusing statement, but it is not. All you need to do is very careful. So let's start with I1. What does that mean? So that means cosine theta 1 is equal to maximum F in, see, it says F1 is equal to F, G is in G because G1 is equal to G, and then we have F and then G, both have two norm of 1. And then we say F inner product G. what was this? This was the definition of the minimal angle, right? So theta 1 will be our minimal angle. Okay. So assume that we call whichever f and g that maximizes, or call f1 and g1 the vectors, call the vector from subspace f as f1 and call the vector from subspace g as g1, that maximum, that has the maximum inner product. Let's call them f1 and g1, okay? Let's keep that in mind. And then I'm going to do this. I will define, let's say that I is now 2. If I is 2, I will say cosine theta 2 is equal to maximum f1. What is f1 in this case? Here, f1 will be, sorry, f2. f2 will be f1 perp intersection f1. And f1 was simply f. In other words, f2 is f1 perp intersection f. So what does it happen? So think about f1 and get the complementary subspace. Okay, so basically the perp intersection f is going to give me the complementary subspace of f1. Okay, and now I'm going to do the same thing in the complementary subspace f1 of f1 and g1. And I will repeat the same thing. So it seems confusing, but it's not. What you need to know is that when you have multiple subspaces, you have multiple angles that you can define. The number of angles that you can define is based on the dimension of the subspaces. Okay. I hope this was clear. That's important. Let's remember the topological space. I'm going to make you a little bit confused, but if you fully understand what I'm telling, it's really fun. Let's remind ourselves, a topology on a set X is a collection T of subsets of X with those 4 properties. We said that if you take any 2 subsets in T, and if you look at the intersection of any 2, then that intersection must be also in T. Or you can take any number of elements of T and look at the union of them. And the intersection, I'm not getting a, I'm just, for intersection, I'm getting only 2 members. But for union, I can get any members, any number of members. And if the union is also in T, that satisfies the property 2, empty set must be in T, and the whole set must be in T. And we said that a set X for which a topology T has been specified is called a topological space. More precisely, we say that there's an ordered pair of the set X and the collection of its subsets T that satisfy those 4 properties. And we also defined what an open set is. If X is a topological space with topology T, we say that this a subset U of set X is called an open set of X if it belongs to the collection. And here is an example. We said that if X is A, B, C, this is a topology Y. If I take any 2 elements like A and B, if I look at the intersection, which is A, and A is also here. If I look at the union is A and B. Union of A and B is what? A and B, which is also in T. If you do the same thing, for example, here, if I get this, and if I get this, and if I look at the intersection, which is B, and B is where? Also in T, okay? Or if I take, let's say, if I take this guy and this guy and this guy, if I look at the unions of all of them, which is A, B, C. In other words, the set itself, and the set is also included here. So that's a topology. Clearly, that's a topology for this set X. Similarly, this one too. And how about B and C? Is this an open set? Well, with respect to this topology, yes, that's an open set. Why? Because that is included in T. But with respect to this topology, that's not an open set. Okay? So any subset of X does not necessarily mean that's an open set. It's open set if and only if what? It belongs to the topology there. So now let's be careful here. If X is a topological space with topology T, and if Y is a subset of X, so now we have X and Y is a subset of X, okay? All right, then think about this. T included all open sets, right? All open sets, because the elements of T are called the open sets of what? X. So T includes all open sets. If I define a new topology for Y that consists of Y intersection with all open sets, Y intersection with all open sets of the original topology, then, because I know for sure Y intersection U is a subset of what? Y, right? That's a subset of Y. Y intersection U is a subset of Y. And it also satisfies the topology, that's those 4 rules that we have for being a topology. If you check it carefully, you will see it. Pause the video and check it. For example, if I get an element, let's say Y intersection U1, if I take another element and if I look at their intersection, okay, their intersection, this will be what? Y intersection U1 intersection U2. And I know that this is in what? T, because it must satisfy the condition of being a topology. And then Y, let's say that this is U3, and Y intersection U3 is in TY. Okay, so if we check each one, they will be all satisfied. Okay. So to sum up what I say, X is a topological space with T, then Y is a subset of X, and then I define a new set of collections this way, then this is a topology on Y, and we call this subspace topology. Okay, so this is topology T, this is subspace topology, and with this topology, Y is called a subspace of X. Well, X was topological space, and Y is a subset of it. This is topological space, and Y is a subspace of X with this topology. Okay, so what's a manifold? I'm just giving introduction to you. A manifold is a mathematical space that resembles to the Euclidean space of a specific dimension. What does that mean? On a very sufficiently small scale. Think about this. Think about this circle here. If you zoom it in, and if you look any point on the circle, okay, and if you zoom in, any point on this circle can be approximated with a line. I mean, in a very small scale, if you zoom in, then the circle becomes just very flat and it's just like a line, okay? Similarly, if you take any point here, and if you zoom in as much as possible, that point will look like a what? A line to you. So basically, a circle, this one, or any other curve is a one-dimensional manifold, because in a sufficiently small scale, they look like a line. However, here, think about this donut, okay? And if you take a point here, and if you zoom it in a sufficiently small scale, it will look like a plane. Similarly, on a sphere, if you take any point, and if you zoom in, it will look like what? Again, a plane. So that's a two-dimensional manifold. Okay. So manifolds are like curves and surfaces, except that they might be of higher dimension. So that's basically what I'm trying to say here. N-dimensional manifold is an object modeled locally on as Rn. Okay, so again, when we have the donut, if you take a point very locally, it resembles to what? To R2. Therefore, it is two-dimensional manifold. Let's talk about linear mappings. And when we deal with finite dimensional spaces, subs or spaces, we simply use ideas from linear algebra. Everything is so simple. However, when we talk about infinite dimensional subspaces or spaces, we need to be very careful. So let T be a linear map on a vector space V. What does that mean? A linear map means, I think there's a delay in the video. Okay, here you go. The linear map means if you take V and W, two vectors, and if you have two scalars, and if alpha V plus beta W, which is a new vector, again in V, and if I apply mapping on this, if it is the same as applying mapping to individually to V and W, and then do it this way, so that's a linear map. Okay, basically, this guy is equivalent to that one. Okay. For finite dimensional spaces, sorry, this linearity is sufficient, but for infinite dimensional spaces, we need one more condition. Okay. Here, think about a linear map from V1 to V2. V1 and V2 do not have to be finite dimensional spaces. They may be infinite dimensional spaces. And we say that this linear map is bounded if we can find a K, a number K, okay, such that, look at this, first of all, I hope you understand this. Even though they are infinite dimensional, let's assume, I'm just making this one up, assume T is from R10 to R15, okay? Then when I say take a V in R10, when I say TV, that means this is in R10. Get the norm in 10-dimensional space. And then, this is 15-dimensional because TV will be in R15. And V is, when I take the norm of V, that means I need to take the norm in 10-dimensional space. If this is equal, less than or equal to K, then this is bounded, okay? And if I look at the minimum of all such Ks, okay, the smallest of such K is called the operator norm, okay? So think about all Ks that satisfy this condition and get the minimum of those Ks. That's called the norm of the linear mapping, or the operator norm of the linear mapping. Here's an example. Think about T from continuous functions space to continuous function space. So if you recall, CAB is the set of all continuous functions. Basically here, this is F, such that F is continuous on AB. Okay, so that's what it is. Now, and assume that this linear map takes a continuous function and it generates another continuous function, x f of x. That's why it is from continuous functions to continuous functions, okay? So let's see. First of all, is this linear? Well, if I do this, T alpha f of x plus beta g of x, this will be what? Alpha x f of x plus beta x g of x, and this one will be t f of x, and this one will be t g of x. So that means that is linear, okay? So that's linear. Okay, is it bounded? Well, is it bounded? Let's check it. Let's get this t f of x. Remember, for continuous functions, we define a norm as the maximum value of the function there, right? So let's see, this will be x f of x, and this will be less than or equal to b times f of x, right? So yes, it is bounded because we know that x is between a and b, and if I take b, or absolute value of b actually to be more precise, okay, if I take the absolute value of b, then yes, then we have a k. So that means that is bounded, okay? So this is what it says. T is well-defined, linear, and bounded. Okay, now let's see. Think about f being a linear function. What does that mean? F is linear function. That means f alpha x plus beta y is alpha f of x plus beta f of y. So that's a linear function. Let's assume that f is a linear function. And let's think about the range of f. Remember, range is a set. It consists of all values that the function takes in its range. And what is the range? In its domain. So this is the domain, okay? And this is the range, okay? So for every value, for all x in the domain, think about all possible function values. That's the range. And that's a set, okay? So the range of every linear function is a subspace of Rm. First of all, are we sure, are we okay with this, that this is a subset of Rm? Yes, because x is in Rn. If I apply x to f, I will end up with a value in Rm. That means the set Rf is a subset of Rm, okay? How about, is it a subspace? Well, is it a subspace? How do we know a subspace? If I take two elements, and if I add them up, okay? If I take an element in this one, let's assume fx1, if I take another element in this one, let's say this one, if I add them up, okay? And since f is linear function, it's going to be equal to that one, right? So that's also in the what? Range of Rf. So that's closed with respect to vector addition, similar for, of course, scalar multiplication. So that's a subspace. So the range is a subspace of what? Rm. Similarly, we can also show that every subspace of Rm is the range of some linear function, okay? Think about, for example, think about any subspace of Rm. Assume that we call it U. It's a subspace of Rm. You can show that U is a range of some function. You can always find a linear function for which U is the range. Therefore, subspaces of Rm are sometimes called linear subspaces. So when you hear linear subspace, you should always think about that they are subspaces of what? Rm, okay? What's an affine space? Well, think about this line. This is a subspace of R2. How about this line, which doesn't pass through origin? That's an affine space of R2, okay? All right, or think about this plane that passes through origin. That's a subspace. But if you think about a plane that doesn't pass through origin, that's an affine space, okay? And it's like shifted version. And well, every affine space can be considered as a subspace in one higher dimension. but I don't want to get into that. But if you say affine space, you should always remember that, hey, you have a subspace M, and then you have a vector V. And if you add V and subspace M, what does that mean? All elements of M will be shifted by V. That's an affine space. And here are some references. I hope this presentation is clear. And I hope you understand the concept of subspaces. In the first lecture, we talked about mathematical spaces. Now we talk about subspaces. And later we'll give fundamentals from linear algebra, and then we'll talk about subspace clustering. Typically, in typical high-dimensional data analysis, we think that data points come from a single large dimensional space. But there are many engineering and science applications in which data actually does not come from one single high-dimensional space, but it comes from a union of subspaces. For example, motion segmentation or facial expression recognition are examples of subspace segmentation problems. So now, after a little linear algebra, we will be ready for subspace segmentation problem. I hope you enjoyed the class, or this lecture at least, and I'll see you in the next video.